Welcome to the module Data Dimension, and in the first lecture of this module we'll be understanding how we can perform feature selection. And for selecting the features we have different techniques, and first of all in this lecture we'll be studying how we can use a correlation matrix, or you can say a heat map, to find out the best features possible to predict the outcome. So for that I have chosen a data global heat index. Okay, so first of all we'll be loading our libraries, then the data we have, and now let me show you the data. Okay, so you can see, okay, just put it 10 now. Okay, so you can see that this is the particular data that we are given. The outcome is the solar radiation. That is, we have to predict the solar radiation in a particular region based on the time of that particular area, the temperature, pressure, humidity, wind direction, wind speed. All these parameters are given to us so that we can predict the solar radiation in that particular area. Okay, so as you can see in this particular case, if we have a higher temperature in a particular area, that means in that area we have a higher solar radiation. That's why the temperature is raising so much, right? So these are the kind of correlations that we have to find out using the heat map. So let's move on. First of all, let me just show you the information and the data description. Okay, so that's the data info we have and the data description. Okay, so that's the data description. But now let me show you one thing also. If we have, say, so you can clearly see that there is no solar radiation in these particular hours, that is before till 0 to 7 we have no solar radiation, because at that time it's a night time. Okay, and then after 6 p.m. also we have no solar radiation. So we have solar radiation only in the time interval of 8 a.m. to 5 p.m. right? So we have to remove this unnecessary data that we have, because we cannot be predicting any solar radiation using this data. So these are the solar radiation values that we have to predict. So we'll be choosing that much data and we'll refine our data so that we can train our models in a best way possible, right? So now we have to clean our data. So what we'll do is we'll remove the data before 6 a.m. and we'll remove the data after 6 p.m. So for that, let's name it as clean 1, and I'll put the data which is before 6 a.m. in this particular clean 1 data. So data, and which column I want the R column. Okay, so it should be less than 6. And similarly I'll prepare another data clean 2, and what I want, the data should be such that the hours should be greater than 6 p.m. Sorry, it should be 18. Wait a second. Yeah, right. So here we have our data with us now. So what we'll do is we'll drop these two particular data, clean 1 and clean 2, from our normal data. So clean 1, let me show you. Clean 1 dot head. Sorry, it's yeah. So you can see that we have all the time in which the hours is before 6. So 0, 1, 2, 3, 4, 5, again 0, 1, 2, 3, 4, 5 for different days and different year, different month. Similarly, we have clean 2 with us. Right? And that's the data after 6 p.m. So 19, 20, 21, 22, 23, and then again 19, 20, and the cycle repeats on for the data intervals we have. Right? And now what we have to do is we have to drop these two data sets, clean 1 and clean 2, from our main data. Okay, so that's very simple to do. Data equals to data dot, what we have to do is we have to drop the data. So we'll say drop. Which data to drop? First clean 1. So we'll say that, so we are given these indexes 19, 20, 21. So based on these index value, we'll remove the data from our original data, right? As simple as that. And then mentioning the x's. So x's will be 0 and similarly we'll drop clean 2 as well. Okay, so now our data is refined. So let me show data dot info. So data dot head. Okay, so now you can see that we have a refined data with us. If let me show you with 10, 20. Okay, so you can see that we have a refined data with us. We have the values of it. This 6 and 7, I have kept it as a margin so that if in a particular region we have a solar radiation, then we won't miss that case out. Otherwise, we can remove this also if you want to do so. Okay, and now since our data is clean, we have to prepare the input and output values for the training part. So you can prepare your input and output data over here, but in this lecture I'm not going to explain you the training part. I am just explaining you how you can select the best features for training your model. So but in this case, let me prepare it to show you how we can prepare the input and output. So for preparing the input, what I want my data, all these parameters, right? Year, month, day, hour, dew point, all these parameters from year till wind speed. But I don't want solar radiation because it would be my output. So for that we have to use data.ilog, right? And then all the rows, but we want only all the columns remaining the last one. So we'll say 0 to 10, but not 10. And then for y, I'll say ilog, and I want all rows, but I want the last column. So -1 means last column. So that's how we can prepare x and y so easily. And then we can fit our data, and we can, because in this data you can see that we have different distributions, different range. So we have to scale our data accordingly. For that we will be using a min-max scaler, which will scale our data from the range 0 to 1, and it will be a non-bias to train our machine learning models, and everything will be perfect. That you can do when you are applying your machine learning models. But first of all, we have prepared this x and y. Y will remain the same, that is output that we have to predict will remain the same, but the input that we want to give to our machine learning models should be such that each and every feature should contribute something good so that our machine learning models can learn. And to analyze that, we'll use a correlation matrix. Okay, so let me name it as correlation matrix. Okay, and I'll say I want to find out the correlation of my data, so data dot correlation. Okay, and then I want the top features that we have, right? So this correlation has different features values. So what I'll do is I'll name it as features equals to correlation matrix dot index. It will tell you all the features that the correlation matrix has worked upon. Okay, so it has considered all these features and have find out the correlation matrix from that. Now we'll perform our heat map, so which is very important. So what I'll say is I'll say data, and then which features I want. I want the features that correlation has worked upon, and I want correlation for that, right? And I want the annotations, that is the labels with my heat map as well. So I'll say true. So wait a second. Okay, let me just increase the size. For that we'll say plt plot, matplotlib we are using, and then using the figure we can mention the figure size that we want. So it is simple, fig size equals to 20,20. So here it is. Okay, it's too big here. Wait a second. 10 equals 10. Okay, so you can see that's our data, and if you find the other parameters correlation with solar index, you can clearly see that in case of Solar radiation, the temperature parameter is highly correlated with a maximum percentage of 61%, and it's a positive. So that means you can use this parameter for predicting your solar radiation very well. And in case of wind direction, the ratio is 17%. So that means you can clearly predict your solar radiation values. And the negative parameters, they are not so important. So you can remove year, month and hour from your data, right? So this is how we find the correlation and we choose the best feature possible. So in the next coming lectures, I'll be showing the next important techniques to select the features which are important to predict a particular outcome. And in this lecture, we'll be talking about extra tree classifier. That's a third technique using which we can find out the most optimal way to choose the best features so as to predict the outcomes. So we aim to find out the parameters which are highly dependent on the outcome, or you can say on which the outcome is highly dependent. So we have to find out these correlated parameters with respect to the outcome, right? So I have imported the library, and the only change I am doing is that I am importing extra tree classifier. It's basically a model which builds up a tree, and that tree is built up based on the importance of that feature. It calculates it and then it builds up it. Okay, so I'm loading the library. Then that's the data. That's the data head we have. Okay, so it's the same data we have used in the previous two lectures of feature selection. Then the data info. We are cleaning the data in the similar manner, right? And then input and output as we have done in the previous lecture. And now what we have to do is we have to use this extra tree classifier. So I have already imported it above, and then I'll say model equals to extra tree classifier, right? So that's how we initialize the model. Okay, so the model is initialized, and now we'll fit our input and output data to this model so that we can calculate the parameter correlation. So x comma y, here we go. It's fitting up the parameters based on their importance. The maths is going behind, and in the meanwhile what I'll do is I'll prepare the data. So let's name it as features, or let's say it as importance. So important equal to pd dot. Now we have to build up the series so that we can visualize what our model has done. So I'll say the model name is model dot, and then feature importance. So feature importance, and that's the feature importance I have. So, and then index equals to the columns we have, right? And then let's print the importance. Okay, wait a second. Its importance is okay. Yeah. So now you can see that's the feature importance it's giving to us, right? And you can clearly see that the temperature is having the highest importance out of all the parameters. So it's performing exactly like we did in the correlation matrix in the lecture 1. So you can say that temperature is highly dependent with the global heat index. We can also visualize our results. For that, what we have to do is simply use this IMP. Simply use this IMP. Then what I want the n largest, say 5, then dot plot, and which kind of graph we want. For this particular data, bar graph shows the best. Okay. Yeah. So that's the 5 topmost features which are highly correlated with the output global heat index. So temperature, pressure, relative humidity, R, and then wind speed, right? So using all these techniques, that is what we have done till now. We have used the chi-square test in the select k-best method. Then what we have done is we used the correlation matrix. Then we are using extra tree classifier. So using all these techniques together can validate our results and we can be sure about the importance of each parameter in predicting the outcome. So this is how we find which parameters or which features are important for us to predict a particular outcome, right? So you can see that these are the top 5 features. So when we are training our machine learning model, we can feed only these 5 features as the input, and the output will remain same as it is, it's obvious, but the input data we have to feed will be more refined, and our models can much more easily predict the outcome value based on the parameter values we are giving to it, right? Also, one more thing, that when we are using this model, what you are doing is you are reducing the features, you are reducing the parameters we want to predict our data. Initially we were having 9 parameters with us, but we can use only these 5 parameters to predict the value, because rest of the 4 will not hold so much of importance, right? If I plot this, wait a second. So you can see that how much less values these columns have. So you can drop these features and use only the top 5 features to add to predict your value. I'll be giving you the intuition behind using chi-square test. In the next lecture, what we'll do is we'll basically use the method select k best method so as to find out the best features possible to predict a certain outcome. And to select those features, we have to use a special matrix in select k best method. So the matrix we'll be using is chi-square test. So in this intuition video, I'll be showing you how chi-square test is being performed and what is the use to do so. So what is the use? Basically, this test is used for categorical features in a data set. Okay, so whenever we have a categorical features in the data set, this chi-square test works perfectly fine for that. It basically calculates the square between each feature and the targeted feature and select the desired number of features with the best chi-square scores. So the higher the chi-square value will be, the more desired the feature will be. That means that feature will be having more say in predicting or in directing towards a certain outcome. Okay. So that's the formula which we'll be working on in chi-square test. It's basically the observed frequency minus the expected frequency raised to the power of 2 by expected frequency. So what we are talking about is frequency is this is basically when we are choosing a parameter, then according to this formula, okay, and there is a summation over here from I0 to the number of entries we have. So it's basically the observed frequency minus the expected frequency raised to the power 2 by expected frequency. So how this formula works, just understand. In feature selection, the main aim to perform is that we want highly dependent feature. So by highly dependent, it means that there should be high dependence between the feature and the expected outcome. So when two features are independent, the observed value is close to the expected count. Basically, the more variate a feature is with respect to the outcome, the more will be the chance that that particular feature will be telling us about the outcome. So if the feature and the outcome are not so much variant, then the observed count will be equal or close to the expected count, and in that case we will have a small chi-square value, right? Because we'll be having a small numerator value above and the expected value is as it is what we have been taking. So observed minus expected will be a very small value if both of these values are similar, and when they'll be very close to each other when the features are independent. So the more lesser the value, the more the independence in features. So we want a high scale value which will state that the independence of the two features is not present. That means those particular features will be dependent on each other. So if there is a huge variation between the parameter and the outcome, then the observed value minus expected value will be a huge value, and in that case the chi-square value will rise, and the higher the chi-square value, the more dependent the feature is, more dependent on the response, and that particular feature can then be selected for model training. So this was the basic intuition behind using the chi-square test in select k best method. In the next coming lecture, we'll be using this particular matrix on a hands-on code on our dataset so as to find out the best features possible. So for that, the next technique that we'll be talking about is select k best. So this technique will help us to choose the best parameters by assigning it the chi-score value. Okay, so we have to find out the chi-score, and then this matrix will be used by the select k best method, and we'll be finding the best parameters that can predict our outcome well. So for that, what I have done is I have already imported the libraries. So these are the basic libraries, NumPy, Pandas, and the important ones are select k best method library and chi-square method. So we are importing it from the module feature selection in scikit-learn. Okay, so let's load it. And then we have the same data that we have followed in the previous lecture so that you can tune up the results and see how the techniques are working on the similar data itself. Then we have the data head, data info, and the data description. As we have cleaned in the previous lectures, because before 6 AM and after 6 PM, we have zero solar radiation, so we can remove this data to as to refine it. Okay, so that's the data we are removing. So clean 1 is this data, clean 2 is this data, and now removing both clean 1 and clean 2. So the final data we are left with is this, and then we have to prepare the input and output values that we have done in XY. Now when we are finding the chi-square, when we are applying this test over our data set, then the very important thing that we need to follow is that all these parameters should have a similar range so that they won't create any bias in our data, right? So why I'm saying about bias is because the very working of this model depends on the formula where we have to subtract the observed value from the expected value, and then the whole square is divided by the expected value. So the thing is that what we are targeting is basically, when we are talking about finding the most important feature, then in feature selection we aim to select the features which are highly dependent on the output. So when two features are independent, the observed count is close to the expected count, and which will make the chi-square value smaller, right? Because what we are doing is we are subtracting the observed value from the expected value. So if the features are independent of the outcome, then the observed value will be close to the expected value, right? Because there won't be any variation. And when we subtract these both values, it will give us a smaller chi-square value. So if we have a high chi-square value, it indicates that the hypothesis of independent is incorrect. And what it means is that feature is more dependent on the outcome, and it can be selected for the model training. So the higher the chi-square value, the more the dependence of feature and the outcome is present. So we have to find out those features on which the parameter is highly dependent on, because in that case only we can easily predict our outcome, right? So this is what we do in chi-square test. We have scaled our data. These are the columns that we'll be talking about, and now we have to use that chi-square technique. We have to code it. For that, you have seen that we have already imported the data, right? And now we'll use this select k best method. So we'll say best feature equals to, the method will choose select k best method, and then we have to pass on the data, and then we have to use the matrix or the technique that we'll want. So we want how we want to function the score. So we'll say score function equals to chi-square, that is we want chi-square test to apply on the data, and then we want the best 10 features from our data. Okay, so this is how data works, and now we'll fit this model on our input and output data. So best feature, then we have to mention the input and output data. So let's train. We have to fit this model on our data, right? So here it is. The model is working perfectly fine, and then we'll find the scores of the resulting scores of the parameter correlation or the dependency chi-square value. So we'll prepare a data frame so that we can easily see what happened. So I'll say the data frame. I'll prepare a data frame for the scores we have. So the model is named as fit. We have fitted all these values in it, and then we'll find out the scores, right? And then same is the case with, we have to prepare the columns for the values of the scores. So we'll say column equal to pd dot data frame, and then we'll pass on the value col. So we want our values corresponding to these columns. Okay, it's, yeah. And then we have to do is we have to combine this data frame. So for that we'll say, let name it as feature score. So feature score equals to pd dot concat, and what we have to concat is we have to concat the scores and the column in a column fashion, right? So we'll say what we have to combine. We have to combine the columns and the corresponding scores, and all this have to be done in a column wise fashion. So x is equals to 1, and then what we'll do is we'll say feature score dot columns, and then we have to mention the feature names, so the column names. So first will be the feature, and then the other column will be score. Okay, here we go. And then we'll print our data. So we'll say feature score dot n largest. So n largest we have to pass of 10, and what values we want? We want the 10 largest value of score column, right? So that's the data we have. So these are the values this particular data is giving. It's giving a high value for the year column, then relative humidity, then temperature, then hour, then month. And this is showing that year is highly dependent with the outcome, then relative humidity, and then temperature. But when we find out the heat map, in that case temperature was highly correlated with our parameter, right? So this is why what we have to do is we have to keep on using different techniques so that we can be ensure that the parameters we are choosing to train our machine learning models or to predict a particular outcome should be perfectly well fitted. Okay, so as to visualize it, okay, and then simply use pl plot. And what kind of graph we want? As you know, the bar graph, simple and easy. So here we go. We have plotted these values as it is given over here. So this is 504, this is 309, and so on. So this is how we find best features or the most dependent features using select k best method, and in that we are using a chi-square technique which I have explained, and I'll be giving you intuition about this particular technique. We'll learn why to use it, how to use it, and why it is so beneficial when we are talking about cross-validation. So what are the steps involved when we are talking about cross-validation? We're using k-fold. First of all, we have to reserve some portion of sample data. For example, you have a small data, okay, or you can say that if you are working on a single data and you are just performing a training and testing part, then to be assured that your model is not biased or it's just not fitting over the data, you can use a cross-validation technique. So for that, you reserve a small portion of your data, right? So let's say I have reserved 20% of my data for the test part, as we do always, and the rest of it will be the training part, right? So what we do is basically we reserve this portion for the testing and then train our models on this particular training part, and then we test the model by comparing the result with these particular test data, right? So this is how we validate that yes, this particular training is performing well when we are comparing the predicted values with the tested score or tested data. So now let's understand what cross validation using k-fold. So basically we split our data into k number of subsets. For example, you have a small data set, let's say 100 entries only, and if you are splitting your data to a ratio 80:20, then 80 entries will be your training part and 20 will be your testing part. And your model will give certain results and will get a certain degree of accuracy. But how can be you sure that your model has not just mucked up the concept? It should be learning. It should not just fix over the patterns of the data you have. It should be learning. So your hypothesis should not be just based on that particular data. It should be generalized. So what to do when we have such a kind of data set? So in that case, what we do is we split our data into k number of subsets. That's why we say k fold, right? So we split our data to k number of subsets, and then these subsets are in such a form. Suppose this was our original data. We have prepared these 5 subsets. In this, we have prepared this data as our testing part. Then we have used this data as our testing part. So initially we train our model over this training data and test against it. We have some result. So result 1. Then we do the same iteration, but then we train our model from fresh on the given data, and we compare, then we test our model on this test data and find result 2. So all these iterations will be independent of each other, and we'll separate our data in such forms and prepare such subsets and then test our model on these test subsets. So we'll be having R1, R2, R3, R4 and R5 results. And using these 5 results, we can average out or generalize our results that yes, this is the particular accuracy our model has. So this is how we can deal with the data dimensions we have, and we can be sure of our model's training, right? So that's why we perform k-fold cross validation so as to divide our data to k subsets, then find out the results and then cross validate the performance at each iteration and be sure, and yes, our model is working perfectly fine. So that's why it's so important, and this is how we perform it. And in the next coming lecture, we'll be performing a hands-on code using this k-fold technique. A data which is not enough to train our models, okay? Then in that case, if we train our model, there might be a chance that the model has not learned the concept, but it has just mucked up the data, and the result it will produce will not be a journal result. It will be dependent on that data set only. And in future, if you test some other data, then the results that model will give will not be credible. So to add credibility to our work, or to be assured that yes, our model has worked perfectly fine, we use k-fold validation technique. As I have explained you in the intuition video, this data divides the data into different training and testing parts and performs the iteration so as to be assured that yes, our model is working fine, or these are the results as per the data change. So we'll see all that stuff in this lecture. So I have already imported my libraries, that is pandas, the basic ones, pandas, numpy, matplotlib, and then I'm using pre-processing module for the scaling techniques. Then I'm using the test split to split out data. Then random forest regressor to predict, and mean squared error to test the results we have. Then I'm importing k-fold using the module model selection, and then I'm importing my data data sets, because in this lecture we'll be using a predefined data set, that is a Boston housing data. So let's name the data as data equals to datasets dot load Boston. Okay, so that's the data we have. Now let's print the data. So that's the data. These are the input values, and this is not a data frame, that's the array notation. Let's check if we can use a data frame over that. So pd.data frame data. So it's okay. So here we have our inputs, we have our target. It's not a data frame, it's in the form of array. And if we check the features we have, these are all the features present in this data. It's clearly describing that we have a Boston housing Boston house prices data set, and these are different instances we have. So it's all telling about the features and the column we have. Okay, now what we do is we'll separate out the input and output of our data. So X, so input, let's name it as X, and it will be data dot data. Okay, and then X. Why I'm doing this? Because it's clearly given that we have two components in this data. One is named as data and the other one is target. So we'll assign target to the output, that is Y, and assigning input to the and assigning data to the X. Okay, and now we'll be importing we'll be preparing our output as well. So our output will be Y equals to data dot target. Okay, completely fine. So also let's print it. So that's the targeted values we have. So these are all the parameters we have, and these are the corresponding labels. So if it's instance 1, then the output to this instance is this value. Okay, so now we have our input and output with us. Let's find out the features we have. So features equals to data dot feature names. These are inbuilt functions that are associated with this data in scikit-learn. So I'm using that, and let's print these also. So these are the features we have. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 features, and corresponding to that 13 features, we have the corresponding output in the target values. Okay, now our target is to split our data so as to train, right? So let's split. For that, we are preparing the components: xtrain, xtest, ytrain, and then ytest using the train test split module. So train test split, passing on the input and outputs. So our input is x, then y, and then test size equals to, let's be at a ratio of 80:20. Okay, so here we go. Now let's check the shape of our data. So xtrain dot shape. Oh, sorry. Okay, let's correct it. Yeah, so we have 404 entries in training, and we have 13 columns as their input. So now you can see that how less our data is. So to ensure that our model is working fine, we need k-fold cross validation. At first, I'll not use k-fold. I'll just give this data to the machine learning model and we'll compare the performance with or without k-fold technique. Okay, so now what we'll do is we'll use a random forest regressor and we'll compare it with or without k-fold. So we'll say random forest equals to random forest regressor, and let's set the ensemblers to be 100. Then we have to fit our data over the training data we have. So rf equals to rf dot fit over the training data we have, that is xtrain and ytrain, and then we'll say predict the values. So let's name it as predictions equals to rf dot predict. What we have to predict is we have to predict the xtest values. Okay, so here we go. We have our predictions with us. Let's check the shape of predictions. Predictions dot shape. So we have 102 predictions with us. Okay, so now we'll find the mean squared error. So mean squared, we have already imported this above. So mean squared error, we have to pass on the parameters. So we'll pass the y test and we will now compare it with the predictions of our model. So it's predicting with an error of 6.6 over here. Okay, now we'll perform our cross validation technique. For that, we'll say, let's name it as k-fold only, and now we'll import our k-fold. So k-fold model we are initializing it, and then we have to pass off. So we are splitting our data into 5 components. That means we are performing 5 iterations with different sample of training and testing output. Okay, so n splits equals to 5, and then let's set random state equals to 0. Then we'll shuffle our data. No, we don't want to shuffle our data. That means we follow a fixed data, and then we'll take out the components keeping without shuffling it, so that we can be sure that the training part in the previous data is not this the testing part in the previous data is not the same now. Okay, so k-fold model is ready. I'll show you how the data is being split over here. So let's name it as train index. Okay, and then test index in k-fold split, because it will be returning 2 values. So I have prepared train index and test index. So k-fold dot split, what we have to split is we have to split the x data, and then we'll be printing our train value and test values. Let's see how. Okay, so now you can see that we have our train data. So now we have our training data, testing data, then the second partition we have training data, testing data, and so on till 5 partitions. So we have 5 partitions with us, and our training and testing models are ready now. We'll pass these data to our machine learning model and we'll compare its performance. So let's again prepare a random forest, a fresh one. So rf1 equals to random forest regressor. Okay, and then for error we'll prepare the list so that we can see how it's performing. So again, for train index, test index in k-fold dot split, k-fold dot split x, and now the work begins. So we have x train comma y train, x train and x test, right? X train and x test in x train index and in test index, right? And similarly we have our y train and y test in those particular index values. So train index and y test index. Okay, so let's initialize the model. So rf1 dot random forest, it will at each iteration it will initialize separately. Okay, so it will work unbiased for all the data sets we have. So random forest regressor, yeah, and then similar part rf1 equals to rf1 dot fit x train y train, then prediction equals to rf1 dot predict x test, and then error dot, we'll append all the results in this error list. Error dot append, again let's copy this, means get error y test prediction. Okay, it's name prediction over here, so here we go. Wait a second, spelling mistake. So the model is trained now, and let's check the errors we have. So that's the results we have. For the partition 1 we have error 7.72, for second we have 12, then 16, then 48, then 22. So now you can see that why we say that using a small data set is not good for training a machine learning model, because in that case it will mug up your results. And using k-fold cross validation, you see that how the results are varying based on the training and testing data sets you are giving, because the data is very low to train a model, and in that case it's not finding out all the logics or it's not finding out the best hypothesis to fit your data. So if you have such a low data and you have to use a machine learning model, then applying a k-fold technique, after applying a k-fold technique, you can, what you can do is you can take out the mean or average out the error of your models, and you can say that that's the error results of our model plus minus certain value, so that you can be certain that yes, your machine learning model is working with this error and in this range, right? So this is why we use a k-fold cross validation technique, and this is how it works. PCA is an unsupervised non-parametric statistical technique which is primarily used for data reduction, or I say data dimension reduction. The target is that we need to reduce the dimensions of our data. In case of high dimensionality data, the dataset has a large number of features. So the primary problem associated with high dimensionality is that the model overfits, which reduces the ability to generalize beyond the examples in the training set. So we target to reduce the dimensions of our data. It can also help us to visualize the results or the data itself, right? Because in case of higher dimensional data, the part or the process of training data becomes very expensive, or it's become exponentially hard computationally. So what we try to do is we try to reduce our data to get out the extract of high dimension and to fit it into a lower dimension data. Also, it is used to filter noisy datasets. For example, in case of image compression, so the target is to remove the noisy data, right? So let's see how principal component analysis works. One more thing, that this particular technique, this is an unsupervised model, and there is a lot of math going behind this model. So there are eigenvector, eigenvalues. This kind of mathematics is involved behind this algorithm. So you don't worry about that. You just understand how it works and how it makes our work simpler. Okay. So starting with our lecture, we'll be importing our libraries, NumPy, Pandas, Matplotlib. That's the basic one. Remaining one we'll be importing as we need them. So loading the data, libraries. Now the data. So I'm again using the data set that we have used in the previous section, that is the feature selection method. PC also selects the feature efficiently and then performs the work. Okay, so data.head. So as you know, we have to predict the solar radiations. Then the data info, 17,520 entries. Now we have to clean our data because there is no solar radiation readings before 6 AM and after 6 PM. So we'll be removing this. This is the clean one data before 6 AM, and then I can show you the clean 2 data, that is the data after 6 PM. Okay, so we are dropping both these clean 1 and clean 2 from the original data. So our data is refined now. Let's check the data description. Okay, and now the data head. So now we have total of 9,490 entries with us. Okay, so now what we'll do is we have a clean data. Now we'll prepare a training and testing part for our data set, and then our target is to feed it to a k-mean data. Then I'll be reducing the dimensions so that we can see the plotation of our data. Okay, so for that what we'll do is, now first of all we'll prepare our data, training and testing. So for that I'll say x equals to data dot ilog, and then all the rows. Now columns 4:10. We don't consider this column, we are not considering this column year, month, day, hour, because they are not relevant over here. Okay, and then dot values. Okay, so y equals to data dot ilog, all the rows and only the last column, so that is the 10th column, dot values. Okay, so now we have to reshape our data because it will be in the form of an array. So we want it in the form of a column. So we'll say reshape -1, 1, that is column axis. We want a column axis, so we are reshaping it. Then we will split our data to training and testing part. So from sklearn dot cross validation import, what we have to import is train test split, right? And then xtrain, xtest, ytrain, ytest. Okay, now we'll be using train test split modules. We'll pass our data input, output, then the ratio, test size equals to, let's say 0.2, and random state, let it be 0. Okay, so here we go. What you can do is you can also use a modern selection module. It will work completely fine. Okay, so our model is, let me show you the xtrain. So xtrain, that's like this, because we are taking only these columns 1 2 3 4 5. So 1 2 3 4 5, also the dew point, so 6 columns. Okay, so we are taking 6 columns into consideration. And let me show you the ytrain also. Sorry. Okay, so yeah, so that's the final column, that is the global radiation, solar radiation, that is GHI values. Now we'll apply the scale. Now we'll scale our data, because we have different range of values in each column. So as to make it a uniform distribution, we'll apply standard scaler technique over the data. So from sklearn dot pre-processing import standard scaler. Okay, now standard scaler, sorry, wait a second. So standard scaler, let's name it as standard scaler x equals to, copying it, standard scaler, and then we will fit transform our data. So xtrain equals to scx dot fit transform the data we have, that is xtrain data. Okay, then the xtest value, so xtest value equals to scx dot transform, because we have fit our data as per the xtrain, so we just need to transform that xtest data. So xtest, okay, so scy equals to standard scaler. Again we have to initialize this because it will perform differently. Okay, so ytrain equals to similarly scy dot fit transform the data we have, that is ytrain data. Okay, wait a second, so it's pre-processing. Okay, transform, sorry, here we go. So we have scaled our data. Now let's see the data we have now. Now you can see the data is from -1 to 1. Okay, and similarly let me show you the ytrain we have. So ytrain is also in the range from -1 to 1. Now we'll apply the clustering technique over our data. Okay, I'll be preparing the clusters from for our data, so as to fixes into a range. What I'm doing is I'll not consider this GHI column. I'm just preparing the clusters which will be suitable for our data. Okay, my basic target is to show you how dimension reduction will work. Okay, so for this, from sklearn dot cluster we'll import the k-means. Okay, and then k-means equals to K means, now the number of clusters we want, initially let's say we want 6 clusters. Okay, don't worry about the technique or how we are using. The target is to show you how PCA will work. Random state, sorry, equals to 6, and then yeah, fine, and then K means equals to K means dot fit. So the training data we have is X train. Here we will not consider Y train as we are doing the clustering part. Okay, so here we go, X train. Okay. Now the labels we have, so labels equals to K means dot labels. Okay, and let's print the labels. So these are the labels assigned to our data. So this data instance will be assigned 0 label, and similarly 0 label is 0th cluster. So this is how the stuff works. Also we can check the cluster centers we have. So for that we can say K means equals to cluster centers. Okay, K means dot cluster centers. Okay, print this way. Let me again run it. I have basically changed the terminology. Okay, so it's the cluster centers. Okay, so now I'll be printing the cluster centers. So these are the cluster centers. These are 6 cluster centers on the basis of which other data points are clustered. So these are the centroids of each 6 clusters. Okay, so now you have seen that we have clustered our data. We have used our data and clustered it into 6 clusters. Okay, now the data dimension is we have 6 features with us and we are clustering them. So if I need to visualize the result, how can I? It's not possible to plot a 6-dimensional data over here. So what I'll be doing is I'll be converting this data, this 6 featured data, to only 2 dimensions. Okay, so for that what I'll do is I'll use from scikit-learn, yeah, and then using the decomposition module, I'll import the PCA, right? And then PCA will be PCA, and the number of components we want, that is the dimensions we want 2 dimensions, so the number of components equals to 2, right? And then we have to fit transform our data, so we'll say we'll fit our X-train data, and then PCA will transform as per the training data. Okay, so you can sorry, if for that it's input, yeah, so now you can see it's again giving an error, it's X-train. So now using the PCA we have converted our data to 2 components only, right? Let me show you the data we have now. So you can see that we have only 2 dimensions. Initially we were having 6 dimensions, but now we have only 2 dimensions with us. For visualizing, we'll use this PCA converted data since it's a 2-dimensional data only. So now we can plot this data very easily in a 2D graph. So understand this code first. For each data we have, each data instance we have, I am plotting it on the basis of labels we have. So since it's suppose X and Y, so what I am doing is I am plotting each of this data the 0th column and the first column based on the labels we have. Data will plot according to the cluster it has, right? So what is this PCA is saying? It's saying 0th column and ith row. It's saying first column ith row. So I am plotting X and Y, and it will be assigned to cluster 6, C16 if it's a part of 0th cluster, then C26 if it's a part of first cluster. This label is equal to 0, equal to 1, equal to 2. These are the labels that we have in our data, and we are plotting this X and Y values based on the data labels we have. Okay, and then we are setting different colors, different markings, so that it is clearly understandable to you. I'll explain it to you again. What we are doing is we are scattering the data sets. I'm applying a loop for all the data we have. So when the loop will apply, it will give the data. So PC is the data we have, and I is the number of row, and 0 is the 0th column, 1 is the first column. So we are plotting X and Y column, and we are saying that if this data belongs to 0th label and this 0, 1, 2 comes from k-means, after applying the clustering, I am saying that if data instance, that is we have reduced using the PCA, if the reduced data instance belong to 0th label, then this data will be classified as C16. If it belongs to second label, it will be C26. So this is how we are plotting X and Y, and we are assigning these pairs to the cluster numbers our model has predicted. Pretty easy, right? So now for plotting, let's set the size. So I'll say RC params, then the figure size. So figure dot fig size equals to, let's say 12,10. Okay, and then we have to set the legends as well for the different clusters we have, so that you can clearly know that to which color belongs to which cluster center, right? So for that we'll use legends, right? And then we have to label it. So we have C16, wait, so C16, C26, C36, C46, C56, and C66. Okay, so for each 6 centroids we have 6 different labels. So let's label them. So cluster 0, okay, cluster 1, okay, we don't need so many, it's already done. Yeah, cluster 1, 3, 5, 6, 4, 2. Okay, so we have 6 cluster labels, and now let's set the title of our graph as k-means cluster, right? Now we'll show the data. Just wait for a second, it's loading. Okay, so these are the clusters we have, right? So you can see that we have brought up our 6-dimensional data to just a 2-dimensional space. So these are the clusters. This is how our data is being assigned different clusters. You can see over here. This is not the perfect clusters for our data. You can improvise the k-mean cluster. You can see your code for over 5 or 4 then 3, because you can clearly see that in this case this cluster 5 is just overlapping over the cluster 2, and that cluster 2 is overlapping the cluster 4. So in this case, there might be a single cluster which can perfectly fit all the data, right? So you can just check the data by using different hyperparameters in k-mean. So when you are training your k-means over here, you can select different number of clusters and see how the performance of your data is. Okay, and also you can clearly see that initially we were having six dimensional data. After applying PCA, we have a 2D data, and this 2D data is being plotted, or it's been put corresponding to the results of k-mean clusters, and it has been plotted as per the results of k-mean clustering, and then we have a two-dimensional space. So this is how principal component analysis technique works. This is how we can reduce our data dimensions. Okay, before applying k-means also, you can still reduce your data, and you can use that reduced data corresponding to your labels and can train to your models. This is your choice. I have used PCA here for my visualizing part. You can use your PCA before training to your machine learning model also. Okay, this depends on your choice or the data you are choosing. Which works better, you can choose that technique. Okay, so this was all for this lecture. So TSNE is one more technique where you can reduce the dimensions of your data so as to visualize and get to know about the hypothesis you can use over that data, or how that data is varying with respect to the parameter. So it is basically a technique to reduce your data, right? So what exactly TSNE is? TSNE stands for T-distributed stochastic neighbor embedding, right? It's an unsupervised nonlinear technique. By nonlinear, I mean to say that the equation it forms is non-linear. That is, you may not have a linear line when you are distributing your data. Why it is important for it to having a non-linear technique? It's because we have to visualize a high dimensional data in different dimensions, and we have to reduce that high dimensions to a lower dimensions as per our choices, right? So the intuition behind the working of TSNE is that we want to see that how the data is arranged in a high dimensional space. So for having that visualization, we fit our data to a lower dimensions, right? It preserves only the small pairwise distance between the data points it has. It basically calculates a similarity measure between the pair of instances. By pair of instances, I mean that if you are given some parameters, say you are given 6 parameters, and then you have to predict another parameter, right? So using that 6 features or that 6 parameter, you prepare an instance, and then you find out the differences between or the distance between the two instances and see that to which pair it will belong to, or what will be the final outcome for that instance. So it calculates a similarity measure between a pair of instances in a high dimensional space and in the low dimensional space, and then it tries to optimize these two similarity measures using the cost functions. You don't go deep into the math behind TSNE because it's a little bit complicated. For this course, you just need to understand that how you can bring your high dimensional data to a lower dimension so as to be clear about the data you are having. So understanding all these concepts, let's move on with our code. So I have used the libraries manifold. This is the module where you have your TSNE. So I am importing TSNE from that. Again, I am telling TSNE stands for T-distributed stochastic neighbor embedding, right? So I have loaded my libraries and then the data we have. So we are using a banknote data. Okay, let me show you the data we have. So that's our data. We have 4 features with us, and then we are predicting the class to which it belongs to, right? So this was a kind of data where we were checking that whether this banknote is duplicate or an original one, right? So whether it's real or it's a fake money. So the class represents real or fake money. Okay, so let me show you the data, the labels we have in class column. So class dot unique. Okay, so we have 2 labels, 0 or 1. 0 means the fake currency and 1 means the real one. Okay, let me show you the data as well. So we have around 1372 entries with us. Now, what we want is we want to visualize our data, but for visualization we have to go for 4 dimensions, right? But we have but our target is to visualize our 4D data to a 2-dimensional space, right? And that 2-dimensional also with 1 dimension as the outcome, and these all input in 1 dimension. So we have to convert 4 dimensions to 1 dimension. For doing so, TSNE works over here. It calculates the distance, similarity measures, and then between the high dimensional space and low dimensional space, and then use the cost function to plot these 4-dimensional parameters to a single dimension, right? So this is how powerful TSNE is. It makes our work very easy. So let me show you. We'll separate out the features and the target column we have. So features we have is the image dot where, okay, then image dot skew column, right, then image dot cut. Don't worry about the parameters that we have. You need not to understand the parameters. You just focus on how TSNE works. Okay. So these are the 4 parameters in our input, and the target output we have is target. Okay. So it's the class column, right? So we have prepared. Now what we have to do is we have to scale our data, because the data dimensions we have, or the range of the values in each parameter, is different. So as I have explained before, to make our model unbiased, we have to scale our data for a uniform distribution. Okay, so what we'll do is, let me name it data norm, that is normalized data. So we'll copy our data to it, because we'll keep with us the original data as well. So we will say, now we initialize the standard scalar we have. So standard scalar. Okay, and then what we have to do is we have to fit our data to the standard scalar, and we have to transform our data. So data norm, and we have to play with the features only. So data norm features, right, equals to standard scalar dot fit. What we have to fit is, we have to fit the data, that is the data features. The original data, we will take the features only. So features, and then we have to transform it also. So we can do it along with this part. So also transform it, and then transform data features. So first we have fitted our data over the data features, then we have transformed the data, and the transformed data will then go to the data norm features. Okay, now what we have to do is we have to plot our TSNE. So for that we have to initialize the TSNE model. It's a supervised learning model, so we have to initialize it. So let's name it at TSNE only. So TSNE equals to initializing the TSNE model that we have loaded above. Then we have to set the learning rate, as we are doing in our machine learning models. You can take example of linear regression, as in that case we have also used a learning rate. So in this case, let's set our learning rate to be 500. Okay, and the number of components we want. So I want 2-dimensional. I want to convert my data to a 2-dimensional space. So number of components I want 2 components. So number of components equals to 2. Okay, and then we have to transform our data. So let's name the data as XTNE, because that's the feature data we have. So XTNE, then TSNE dot fit transform. Now we have to fit transform our data norm features, right? This will be the input, so that's why XTNE. And similarly we'll prepare the YTSNE, that is the output. So YTSNE equals to data and the normal targets that we have to predict. So the output column, data targets, right? So it will take some time. Yeah, it's ready now. So we have our input XTNE and the output is YTSNE. So XTSNE is now being converted to a single a uniform data, and when we basically this data norm features was the scale data. It has all the 4 parameters, but those were scaled. Now when we fit transform our data using TSNE, it has converted that 4-dimensional data to a single dimension, and now we have 2 dimensions with us, that is X data and Y data, and we'll be plotting an XY correlation to see the 2-dimensional plotting of our data. Okay, so this is how easy it is. So for visualization we'll use matplotlib. So plt.figure, that means set the size of the figure. So figure size equals to, let's say, 16 by 11. Okay, and then plt.scatter, and what we have to plot is we have to plot XTSNE and the YTSNE. So we'll say XTSNE and np dot where y equal to 0, plotting it with the 0. Okay, and then X TSNE np dot where y equal to 0 with respect to 1, and okay, sorry, right, and then color equals to green. Let's set the marker also. So marker be star. Okay, so marker be star, and again copying this. Okay, so XTNE where this y value equals to 1 with respect to 0, and where y value is equals to 1 plotted with 1. Okay, so let me just explain you what we are doing over here. So initially we were having the XTSNE. So PD dot, let's say, let me show you PD dot data frame. So what data we are talking about? We are talking about XTSNE, right? So XTSNE. So this data was having 0 and 1 dimensions, right? So these are the 2 dimension, and these were rest of the total entries we have, right? So 172 entries, 2 columns. Now what we are doing is we are basically plotting the data, all the data 0 with respect to 0, 1 with respect to 1, 0 with respect to 1, and then 1 with respect to 1. So that's what we are doing over here. That's how we are scattering our data. Also, if we say, let's say plt dot x label and set the data dimension as dimension 1, and then y label as dimension 2. Okay, and then let's title it as the TSNE graph. So TSNE, now plt dot show. Okay, so now you can see, okay, I have done a mistake. The markers are same and colors are same. Let's change it. Okay, so now you can see that's the graph we are finding out from this data. So we have basically converted a 4-dimensional data to a 2-dimensional data. We are plotting our data XTSNE with respect to y, and it's taking each column with respect to the class of y each time. Okay, so what we are doing is we are plotting XTSNE data where y equals to 0 and the data is 0, and similarly where the data was 0 and the label was 1. So we are doing all the pairing and then scattering using the scattered graph. We are plotting that data over here. So now you can see that this is the data we have. This is how we can visualize our data. you can see that in high dimensional space, our data can be easily be separated out using any hypothesis. If we are using a linear hypothesis, you can think about it as in a high dimensional space. It's just an intuition for you to visualize how your data is plotted and how your hypothesis can work. For example, if you'll be having a these red marks over here also, then in that case, to separate out this green data, you have to use a ellipse. So you can have an idea of how your hypothesis work and how your model can be used for such kind of data. Okay, so this is how we use TSNE. This was all for this lecture. This is how we convert a high dimensional data to a low dimensional space so as to visualize that data and to have an intuition that how our hypothesis will work and what kind of model we can use to train over this data. Right? So this was all for this lecture. Thanks for watching this video and keep following.